So first of all, many thanks to Katya for inviting me and for organizing so nicely this series of seminars, which has kept us all in touch. I also wanted to thank the organizers of the Helsinki conference for graciously putting this talk in the program. And I want to apologize to those of you who've heard it before. Katya has encouraged me to give an encore presentation because the first time around it wasn't recorded. So that's my excuse. And also apologize to Katya for making her read such a long title, but the title sort of tells you what I'm going to talk about. It's basically 2 plus epsilon open problems, which we solved in a joint work with my PhD student Idan Regev and Daniel Tataru. This appeared in 2020, earlier as a preprint. So I'm going to start with some nonlinear equations, which was also the theme in the Helsinki conference. Then I'm going to talk about the main object of this talk, which is the scattering transform, which those of you who have worked in inverse problems using the D-bar method are quite familiar with. Then describe our new theorem about this scattering transform, a Plancherel Theorem. Talk a little bit about the proof, because the proof itself involves some new results which might be of independent interest about fractional Laplacians and pseudodifferential operators with non-smooth symbols. And then I'm going to apply this result about the scattering transform to another open problem, which was the global well-posedness for the defocusing Davey-Stewartson equations in the mass-critical case. I'll explain what that says in a moment. And finally, the epsilon, because this wasn't really stated as an open problem, but it's possibly the thing of most interest to you, is what this result tells us about the Calderón Inverse Problem in 2 dimensions. So the Davey-Stewartson equations, I will show you one in a moment. Here, maybe I can show it to you right now. So here the unknown is the function q. It usually shows up as a system, but in this case, if you solve for g, think of g as d bar inverse dq squared, substitute here, then you have something that looks like a nonlinear Schrödinger equation. I should warn you, this is, when you work this out in terms of complex variables, it looks more like a Lambertian than a Laplacian. And the nonlinear term, because of this Bjerling transform, is going to be non-local. So why should you care? Well, they model certain kinds of water waves, right? So you start from the standard Euler equation with gravity for the water wave, beautiful equation, and then with the so-called multiple scale analysis, you introduced fast and slow variables and look for waves in different modalities. In this case, one is looking for waves that are traveling principally in one direction and are weakly nonlinear, and they're surface waves. The same equations arise in ferromagnetism, plasma physics, and nonlinear optics. And what's interesting is they've been shown to have a certain universal character in the sense that you, from a large class of nonlinear dispersive equations, in the limit of weak nonlinearity, you can get this as a representative model. So think about it this way. I learned this from Calderón a long time ago. When we take nonlinear equations, if the nonlinearity are super weak, we end up with linear equations. So the linear equations model everything when the nonlinearity is negligible. Now, if you want to include nonlinearity at least weakly, this is somehow the next least complicated model. For different classes, you get different such nonlinear equations. Now, for dispersive equations, there is a large group of top analysts who work on these. Very sophisticated methods have been developed. And in particular, for this Davey-Stewartson family of equations, where there are about, I think, 4 parameters, various cases of local well-posedness and global well-posedness have been studied and solved. Some nice high-precision numerics have been also done, partly using the methods I'm going to talk to you about. So what's this L2 critical case? Well, these equations have a certain scalar invariance. And you look at the space where the Cauchy data is given. L2 happens to be invariant under the scaling that works for the PDE. So you cannot make tricks of taking small data or small time and playing with scalings. So typically critical cases are harder. And for the one equation which we are looking at, namely defocusing Davey-Stewartson 2, the problem of well-posed, global well-posedness for arbitrarily large initial Cauchy data and arbitrarily large time was an open problem. So here's the equation that I mentioned. I should say, with the methods I'm going to describe, Peter Perry proved global well-posedness, assuming the initial data Q0. So this is a Cauchy problem. First variable here is time. Z is X and Y is space. So assuming the Cauchy data has one derivative in L2 and in a weighted L2, Perry was able to prove global well-posedness. And here we're going to show this just assuming Q0 is in L2, which introduces some difficulties I will describe. So what's special about this this particular Davey-Stewartson equation with these choice of parameters is that it is integrable. In the following sense, it can be written in the form of a lax pair. Evolution in time is a convolution, is a commutator of this operator L, which is going to be important for us, and another differential operator A, which is not so important for us. So let's look at L. This is a little system for 2 functions, M1 and M2. We'll be more precise later, but for now, let's say we'll require M1 typically to go to 1 at infinity and M2 to go to 0. And so given a function Q, we'll see the conditions on Q later. Specifically, just Q and L2 is what we'll want. Okay. You solve for M1 and M2. And then here is the transform that I'm going to talk about. So the scattering transform of Q, which I'm going to argue is like a nonlinear Fourier transform, is the integral. Think of this as e to the I x dot xi. This is it's convenient to introduce this notation, which I had a long time ago, in terms of the complex variables z and k, times q. We're taking q conjugate here for reasons I will mention in a second, and the function m1, which we saw here. So the first reason I'm going to call this a nonlinear Fourier transform is that if you linearize it, so if q is very small, then think of this as 0, m1 is constant, so it's basically 1. If m1 is 1, this is just the Fourier transform up to normalizations. So whatever this transform is, its linearization at q equals 0 is the Fourier transform. A more interesting, much more interesting reason to call this a Fourier transform is this miraculous fact, which may be familiar to those of you who've seen the KDV story, which is the following. Suppose Q, which so far is just dependent on the space variable Z, suppose you take a family of such Q, parameterized by time, which satisfy the Davey-Stewartson equations. And at each time t, you compute the transform S of the Q at time t. Then, if Q satisfies the Davey-Stewartson equation, this transform will satisfy this very simple linear equation. Okay, derivative of the transform in time is just this multiplying S itself. So S is just an exponential in time with a real phase. Now, one reason so there are similar equations to these these are equations in the Z variable. There are similar equations in the K variable. So for this particular problem, similar equations, I should say, with Q replaced by S. So S somehow measures the departure of M1 from being an analytic function in K. And it turns out, because of that the inverse transform is exactly the same as the forward transform here. So whatever analysis we have for the inverse transform, right, you can get Q back from the its own scattering transform S by the exact same formula. That's the reason we put the conjugate here. So whatever we say about S will also be true about the inverse. And so the idea is to try to solve this Cauchy problem as follows. You give me Q naught, the potential Q at time 0. I take the scattering transform S of this potential, that's S naught, so I know this. S satisfies the simple equation in time, which I showed before, this one. So we know what it is at any time t. Well, let's then take the inverse scattering transform of S to get the potential at time t. So we start from Q naught. We would like to solve this nonlinear problem, and we go this way, transform to S naught, solve the corresponding linear problem for S, transform back. So that's essentially solving this nonlinear problem as you would, let's say, the heat equation using the Fourier transform. So that's the second reason why you might call this a nonlinear Fourier transform. All right, a third reason. So this scheme that I just described was first introduced by Ablowitz and Foucault. Bius and Koifman made it rigorous for potential in Schwartz class. And they also showed that as it turns out, the L2 norm of S is the same as the L2 norm of Q, and Q is in Schwartz class. So when you see this, of course, very, very tempting, in fact, I would argue irresistible, is can you show that this is true for any Q in L2? So that was an open problem. Of course, if this were a linear problem, you would be done. But this, so the scattering transform is norm preserving, but it is not an isometry. So you cannot just start from a dense set and try to prove this for all Q in L2. You need the continuity or some uniform continuity, and proving that is as hard as the problem. So this was first done rigorously for Sung for Q in L2 intersect LP, and also condition on Q hat so that he can go forward and backward. Russell Brown proved this identity with Q in small norm, where one can sum up Neumann series and with careful analysis that he did, bypass some of the difficulties. Alex Tamasan also proved sort of Fourier-like properties. Peter Perry, as I mentioned, proved this when Q is in weighted Sobolev space with one derivative. Karyastala, Daniel, and Rogers proved this, improved the Perry result to just requiring epsilon derivatives in a weighted L space with epsilon weight. And then Brown, Ott, and Perry extended that. So, right, a third reason you might call this a nonlinear Fourier transform is because of this Plancherel identity. A fourth reason is, look at this nice result. Q has alpha derivatives in L2 with weight beta, if and only if, as you would expect from the Fourier transform, its scattering transform has beta derivatives with weight L2 with weight alpha. So I'm now ready to state our main theorem. So all the new theorems I'm going to mention are in this one paper with Idan Regiev and Daniel Tataru. So this nonlinear Fourier transform I just talked about, turns out, is bijection on L2. In fact, it's a C1 diffeomorphism of L2 onto itself. It satisfies the Plancherel identity. There is also a pointwise bound, which, as you will see, is quite important for the application, at least to the nonlinear PDE. And here, this denotes the maximal function of the Fourier transform of Q. I will talk about the Hardy-Littlewood maximal function. I will talk about that in a few slides down. So the scattering transform at any K is controlled up to a constant that only depends on the L2 norm of Q by the maximal function of Fourier transform at that K. We have this highly desirable by Lipschitz continuity with the constants depending only on the L2 norms. Inversion theorem is advertised, and also this transform is a symplectomorphism. This is on the tangent space at any, it's sort of easy to see at the tangent space at 0, where it's basically the Fourier transform, but this is true at the tangent space at any potential. It preserves the sort of obvious symplectic forms on L2. So that's the result. Let me tell you a little bit about the proof. Recall how we define this transform. You solve the system from M1 and M2, which I'm now going to modify, make more manageable. And once you have M1, so given Q, you solve this. Once you have M1, you define the scattering transform this way. So Beals-Koifman noticed that you can decouple the system into two scalar equations. So we'll define, instead of the functions m1 and m2, we'll define m plus minus this way, and then each of them separately solve a little d bar equation. dm dz bar is oscillatory term q m bar, and each of them go to 1. So to construct these functions which you need if you are to define the scattering transform, we have this integral equation. And now I can explain some of the difficulties. So remember, we'll want to show that the scattering transform is in L2 of K. So we'll want some m plus minus 1 to somehow go to 0, to have some decay as K goes to infinity. How do you get decay when K goes to infinity? Well, typically by some sort of integration by parts or fancy integration by parts, for which you will typically assume Q to have some smoothness. So this is why the previous results all assumed at least a little bit of smoothness in Q. So our challenge is to somehow find bounds which capture the large K decay just for Q in L2. No smoothness, no additional smoothness whatsoever. And the next difficulty for things like the uniform Lipschitz continuity and so forth, we would like this operator. It's sort of easy to show that this operator is invertible when Q is in L2, but we want the norm to depend only on the L2 norm of Q. And that's a lot harder. Okay, so separately from the rest of the talk, I'm going to show you, talk to you about this result in harmonic analysis about fractional Laplacians, which we particularize to this first term in the integral equation, d bar inverse E minus KQ. So what we will see is that there's an estimate that bounds this for every K in terms of the maximal function of the Fourier transform of Q at K. So the maximal function, most standard one, there's various varieties, just takes the average of, let's say you are at X, you look at all balls, or in this case, disks of radius R around X, take the average of your function, and take the sup over all possible radii. So it's a classical result of Hardy and Littlewood that this is a bounded operator on LP. So if the function Q is in L2, Q hat is in L2, therefore the maximal function is in L2, therefore this will be in L4. So all of a sudden we know that when Q is just in L2, we will see that our functions will decay at infinity as functions in L4 of K. So this is how we capture the decay at infinity. So this is one of our one of the results that I advertised. So this is now true in any dimension. It might be of interest for those of you who work with fractional Laplacians. So here's the, if you wish, the Green's function for the fractional Laplacian. Any fraction here, we're just using alpha basically equals to 1. So it's the square root, like the square root of the Laplacian. So this looks like something that should be in harmonic analysis textbooks, but is, as far as I know, new. It tells you that you can bound the fractional integral of f by the maximal function of f at x and the maximal function of the Fourier transform at 0. And so when you put in this oscillatory term, it changes from Fourier transform at 0 to Fourier transform at k. And this is how we got that. So let me quickly indicate to you, since this is a bold claim, let me indicate to you how we prove this. So you define the fractional Laplacian. On the Fourier transform side, we're dividing by 1 over magnitude xi to the alpha. And then we decompose, we have a Littlewood-Paley decomposition in frequencies localized in annuli of size 2 to the j from minus infinity to infinity. So the main trouble is, of course, when xi is near 0. And when xi is near 0, we use the maximal function of the Fourier transform f hat at 0, right? Which is the sup over 1 over r to the n of all of these. So if you substitute that in this annulus, you will get an, because of this r to the n, you will get a 2 to the nj naught from this, and then 2 to the minus alpha j naught from 1 over xi to the alpha, because that's where our frequency is localized. Now, for larger frequencies, you're away from 0. This is now a bounded multiplier, and then it's known that that can be bounded in terms of the maximal function of f. So we have the maximal function of the Fourier transform of f at 0 and the maximal function of f. And now we optimize about the cutoff frequency j naught and get this inequality. And with this inequality, we're now ready to go. Now, the other difficulty, as mentioned, was to try to invert this operator with norm depending only on the L2 norm of Q. So I won't say much about this, except that this is a technique that we borrowed from the theory of dispersive equations. Using concentration compactness profile decomposition. It's in fact the most technical part of the paper. But while this technique is usually used in the time-space domain, here we're just using it to analyze the spatial scattering transform. So that's the novelty there. And so with those results in hand, we can now construct the functions m plus and minus. They will be in L4, both in Q, so both in Z and in K, and have this pointwise behavior in K, which I discussed. All right, well, we're not quite there yet. Once we have these functions, I'm now recalling the formula for the scattering transform. So we are taking Q in L2, and we would like to prove that the scattering transform is itself in L2 as a function of K. And so from its formula, you can see it looks like a pseudo-differential operator with this function m acting as the amplitude. Now, what do we know? We know this as a function of k is in L4. That's not good enough. We wanted it to be in L2. So somehow we need to capture more of the oscillation. We also know as a function of z, it's in L4. Q is in L2. L2 times L4, that's also not an absolutely convergent integral. So we need to do some work to try to prove that, in fact, this pseudo-differential operator is bounded from on L2. It takes L2 functions of Z, Q, to L2 functions of S. And we do not have the kind of smoothness for the symbol, right? So pseudo-differential operators with non-smooth symbols have been studied in detail. You look up the literature, you look up the book by Kaufman and Meyer, and you won't find what we need. So we have a new result on boundedness of pseudo-differential operators for the kinds of symbols that we have to deal with here. And here's that result. And I'm stating this in different notation because, again, it is completely general. It's true in n dimensions, and alpha can be anything between 0 and n. In our case, it's going to be 1, and dimension n is 2. So it's sort of known that having integral conditions on derivatives of the symbol in the C variable makes it easier to prove bounds on the pseudo-differential operators rather than just the usual typical pointwise bounds in X and C. So if we assume this on the symbol, which turns out to be precisely what we have when for our M1 when n is 2 and alpha is 1, we can prove that the corresponding pseudo-differential operator is in fact bounded on L2. And I won't say much about the proof except to say that it relies on the same estimate on fractional Laplacians that we had before, which makes it rather easy consequence. It also gives us this pointwise bound for the pseudo-differential operator in terms of the maximal function of f at x and the value of the this norm in C at the point x. So now we have all the tools in hand, and that completes the proof of the Plancherel theorem. So let me go back and show you the Plancherel theorem. What I like is there are a lot of conclusions, but the only hypothesis is that Q is in L2, nothing else. All right. So now let's try to apply this to the problem where the transform was first introduced, namely Davey-Stewartson. And so here's the result we have. For the Cauchy problem, in the mass critical case, when the data is in L2, there is a unique solution satisfying the nonlinear PDE in this space, L4, intersect continuous functions from time into L2. It has a uniform bounds, so this comes straight from the Plancherel identity. So the energy is conserved, but also some regularity, namely, it's a function of, as a function of time and position, is it's in L4, controlled purely by a constant depending on the L2 norm of the initial data. There is stability if you have Cauchy data that is close in L2. The solutions of the nonlinear PDE will be close for all time in L2. But this constant, we do not have, so for potentials with L2 norm controlled by R, we do not have an explicit form for this constant C of R. So let me show you something about how we get pointwise control of this solution of the nonlinear PDE coming from the result we had about the scattering transform. So remember how we are going to solve this, right? We take Q at time 0, we take S naught, its transform, we flow it in time, and then Q at time t is the inverse transform of this S of t. Okay, the inverse transform behaves just like S. And so, sorry to go. So the transform, right, is controlled by the maximal function of Fourier. So now, this transform will be controlled by the maximal function of the Fourier transform of this S. It's a little inverse Fourier transform because S is a function of K, and we're taking Fourier transform in Z. Okay, so what does this tell us? This tells us that the solution to the nonlinear PDE is controlled at any time t and any position z by the maximal function of this. Well, let's see what this is. This is the Fourier transform of STK, which is that. And this is basically the solution of the linear problem associated with Davey-Stewartson. So if you look at the Davey-Stewartson equation and you drop the nonlinear term, right, you will have a linear flow, which you can do by Fourier transforms. I'm denoting this linear flow by u at time t. So u at time t takes an S naught hat, which is a potential, right? S naught is a function of K, so this is a potential of position Z. We flow it to time t, and we have the solution of the linear flow at time t and position Z. And what we have shown, and I think this is, as far as I know, the only time I've seen this up to now, where you have the a proof that the solution of the nonlinear problem is controlled by the maximal function of a corresponding solution of a linear problem. Whoops. With a constant depending only on the L2 norm of the initial data. Moreover, for such a linear flow, there are the famous Strickard's estimates, which say that if this is in L2, the corresponding solution of the linear flow will be in L4 in T and Z. And so the point, and if that's in L4, the maximal function is in L4. And so this pointwise estimate allows us to transfer Strickard's estimates for the linear flow to the nonlinear flow. So if this is in L4, Q will be in L4. And that's how we show that the solution of the nonlinear problem will be in L4 as a function of time and Z. We can also prove scattering, which is the next thing you try to understand when studying such nonlinear PDE. So this is scattering for Davey-Stewartson. Namely, what happens for large time. And so let me remind you of the standard definition of the wave operators. So you have the solution, we now have the solution of the Cauchy problem. We started at Q naught. And here it is, this axis is time, and we're going to flow it some non-linearly, just schematically here, for all time. So this is my Q of T and Z. If there is another Q such that the linear flow that starts at Q plus is approximately equal for large T, T goes to infinity, to our nonlinear flow. So if the nonlinear flow we have is asymptotic to the linear flow of some other potential, we call that potential Q plus the wave operator of Q naught. So W, the wave operator, sends Q naught to Q plus, the Cauchy data to the potential, which when flowed linearly approaches our nonlinear flow. And similarly, there's a Q minus. And so you may have guessed it by now, the wave operators exist, and what we have shown is that the potential that you need here can be obtained as follows. You take your initial Q naught, you compute its scattering transform, nonlinear scattering transform. This is the nonlinear Fourier transform of Q naught. But then you invert it as we did here. I'm sorry. You don't invert it with the nonlinear Fourier transform, you just pretend it's a Fourier, you invert it with the linear usual Fourier transform. So take the scattering transform, invert back with a Fourier transform. You will get a potential in L2, we already know that. And it turns out that's the wave operator. So suppose you don't believe in using this machinery of this inverse scattering transform to solve the PDE, and you have another method to prove existence of solutions of the Cauchy problem and to prove that they scatter. Well, this tells you that out there in the wave operator sits precisely this nonlinear Fourier transform we've introduced. So it is really part of the problem. And from our Plancherel theorem, we know these are now surjective operator, in fact, non-preserving diffeomorphisms of L2. So Peter Perry proved something similar for a more restricted class of potentials. Now, there is something called the time domain scattering transform, which is basically what an observer would do looking at this nonlinear PDE from far away. Namely, you start at minus infinity. That's like preparing, think of this picture in the minus infinity. You're preparing a potential Q minus as somehow initial data at minus infinity. You let the problem flow, and you see what potential Q plus this looks like far away. So the map which takes you to what it was before, which is Q minus to Q plus, is the scattering operator, and it's what you observe looking at this nonlinear PDE from far away. So this map is defined as W inverse W plus. Now, it turns out both W plus and W minus are the same object. That means I was actually a little disappointed by this. I was hoping that you would see some of the nonlinear effects show up in the this time domain scattering operator, but in fact they don't. So the scattering operator from minus infinity time to plus infinity is just the identity. So the nonlinearity is invisible from infinity. Okay, whoops. Quick application now of the same nonlinear Fourier transform to a problem you know a lot more about in dimension 2. So the Calderón problem, which has been already described by many people at the conference, does the Dirichlet to Neumann map determine the conductivity? And here is just a quick summary of the results just in dimension 2. I hope I'm not offending anybody. So the most important result is that the answer to Calderón's question is yes for conductivities in L infinity. Now, Karsta and Wang proved that the answer is also yes if the gradient of the log of sigma is in L2 with small norm. And they used Brown's result on the scattering transform, which requires small norm. So we were able to extend this to L2. And on the way, I have a few minutes to describe what this has to do with our transform S. So it's a standard trick when you have this divergence form equation in 2D to use complex variables the way you would factor. Let's say if u is a harmonic function, if sigma is 1, if u is harmonic, du will be analytic. Well, the more general statement for sigma harmonic functions, if you define v in terms of du this way, then v is not quite analytic, it's what's called pseudo-analytic with this potential q, which we'll assume is in L2. And if you compute the tangential and normal components of the solution u at the boundary, you will see that the tangential component is the imaginary part, essentially, of v times the normal. So if we know u on the boundary, we know its tangential derivative, and so we know this. And if we know the Dirichlet to Neumann map, du d nu, then we know the real part of this. So this makes it natural to define, right? Pretend this is like for analytic functions and define a corresponding Hilbert transform. So Astal and Paivarinta did something similar for the Beltrame equation, but here we have pseudo-analytic functions. We're given the imaginary part of the function v on the boundary, as explained before. And our data is the real part. So the map that goes from the imaginary to the real is a Hilbert transform. And from the previous slide, we know that if we are given the Dirichlet to Neumann map for sigma, there's this formula connecting it to this Hilbert transform. So we may assume that we know the Hilbert transform of this Q and try to solve this little inverse problem for a pseudo-analytic function. Given this boundary operator, can we find Q? And the trick is that Q is only in L2, so you need to prove that even the Dirichlet problem makes sense because sigma will now be allowed to degenerate it can become unbounded and also approach zero logarithmically. So the theorem is that if Q is in L2, then we can in fact recover it from this Hilbert transform. So let me quickly show you the connection to the scattering transform. Here's the formula for the scattering transform, where instead of that M1, I put M plus M minus. M plus M minus times Q times this solve, a D of M bar equation. Integrate by parts, and you will see, as is familiar to people, that one can find a formula for the scattering transform if Q is zero outside of omega, purely in terms of the boundary values of these functions M plus and M minus. And so the problem is reduced to determining these boundary values from the given Hilbert transform. And that's done by looking at an exterior problem outside of omega, where these are just analytic functions, and we know their boundary condition in terms of this Hilbert transform. I'll go fast over this. And so our application to inverse problems of the Plancherel theorem I described is the following theorem. Suppose sigma is positive, and all we assume is the gradient is in L2, and sigma is, for simplicity, 1 on the boundary. So this goes a little bit beyond L infinity functions. It allows some degeneracy and some unboundedness. Then for such conductivities, one can recover them from the Dirichlet to Neumann map. And so to summarize the talk, or at least this part of the talk, from the Dirichlet to Neumann map, we have a formula that gets us to the Hilbert transform for the pseudoanalytic problem. From this Hilbert transform, by solving exterior problems or linear equations on the boundary, we can get traces of the solutions M plus M minus on boundary of omega. From those, we have a formula for the scattering transform. So this is a formula. So most of the work is here. Here's a formula, and now most of the work on this side is the given Plancherel theorem, which gave us an inversion in particular from S back to Q. Once you have Q, you can get sigma by just exponentiating. Thanks very much.
Thank you very much, Adrian, for the very nice talk. Are there any questions or comments, please?
I have a quick question. This is your Adrian. Very wonderful talk. I was wondering the results you presented about the time domain scattering theory. In which paper can we find them?
Same paper.
It's the same paper.
Same paper in Invenciones 2020.
Okay, great. Thank you very much.
Thank you very much. Are there any other questions or comments, please?
I have a question.
Please.
Yes.
So you said this describes propagation of some kind of waves, right?
Of which?
The solution describes propagation of waves of certain sort?
Yes, yes.
So it must be real valued then, right? So can you write this as a system for the real and imaginary part with real coefficients?
Right. So they start from waves for the Euler equations, and they use this multiple scale business, and they have an envelope and a phase, and so those are the envelope and the phase are this Q and this G. So those are complex, but they give you the solutions to the So you expand the real valued functions that solve these waves in terms of, or you approximate them by this Q and this G.
But what is the meaning of x1, x2? Those are just spatial variables?
Yes, x1, x2, the spatial, they call it in 2+1 dimension. But the whole method here is, I mean, obviously we use a lot of complex analysis, so we introduce Z instead.
I was just wondering about the meaning of all those variables, right? Before we start analyzing them.
Right. So I should have maybe started from, I'm not a great expert on this, from the reduction of Euler with gravity to how you get to DS2.
Yeah, okay, thanks.
Sure.
Thank you very much. Are there any other questions or comments, please?
Okay, so maybe I should stop sharing and seeing who.
Okay, so one question
Hello,
here.
everybody. Yes, hi.
Please.
Hi. So about the Calderón problem, so do you expect that with this integrability on the derivative, we can go below? We can assume some sigma, I don't know, in I am just guessing, H epsilon for some epsilon, and still we could get a regularity, or does make sense at all, the question? Or, I mean, I know from the proof that this is the natural.
Well, I mean, the connection. So the whole story here is Q is in L2.
Yeah, I know.
I mean,
the result is that
Q in this case is one derivative of sigma, roughly.
Mm-hmm.
So what you're asking is for Q to be in some negative Sobolev space.
Yeah.
For this theory. Don't know.
Okay. Yes, I mean, it was just out of curiosity. Okay, thanks.
Sure.
Right.
So with this, Right.
Okay, thanks. It was very clear and very nice. Thank you very much.
Thanks.
Take care.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please?
Hi, Adrian.
Yes. Hi, Jim.
I've been having a lot of computer problems, but I did hear almost all the talk.
Okay. Which part would you like me to repeat?
No, it's only the last 4 or 5 minutes. So.
Okay.
But that was very good. I understand you've had some practice with it.
Yes. In particular at UCLA, where you couldn't make it. So I did get you in the end.
Very nice.
Thanks.
Thank you very much.
See, there's something in there. And I haven't said, there's various people I should say hi to. John Sylvester, Shari, Tracy, David Isaacson. Hello, everybody. Grisha, Ali. I've said hi to.
Okay, thank you very much. So if there are no any other questions, then thank you very much.
Peter, hi, Peter. Russell, Alex is there.
Okay,
Sorry.
Are there any other questions or comments? Sorry for interruption. If there are no any other questions or comments, then thank you very much, Adrian, once again for the very nice talk. And thank you very much, everyone, for coming. Thank you very much. Thank you.
My pleasure.